And our final speaker will be Jerry Tang, and he is from the University of Texas, Austin.
Hey everyone, I'm Jerry. Today I'll be kind of approaching things from the opposite direction. I'll be talking about mapping and decoding language representations. So I'll start by showing how we decode language using fMRI, and then I'll discuss our efforts to translate this into DOT. As a disclosure, I'm an inventor on a patent application related to the decoding approach. Okay, so let's talk about language decoding. When we produce language, we start with the semantic representation of a concept, and we need to map this representation into words and then motor plans and muscle movements. If this process is disrupted, it can lead to language disorders like aphasia, apraxia, and anarthria. An emerging way to help people with language disorders is to decode their brain activity and predict what they want to say. Recently, there's been a lot of great work on decoding motor plans, and this predicts the movements that someone wants to make. This can be very helpful for people with anarthria and other kinds of paralysis, but it's less suitable for people with higher level disorders like aphasia, since these people might not be able to form motor plans. So as an alternative, we want to decode semantic representations. This predicts the concepts that someone is thinking about. Semantic representations are thought to be spared in most language disorders, so we hope that semantic decoding can be used to help a wider group of people. To decode semantic representations, we need to understand how they're organized in the brain. And so in our work, we access semantic representations using natural language. So here, a person is listening to the story on the left, and it evokes the pattern of brain activity on the right. We can analyze this brain activity using something called an encoding model. So this is a model that takes in some stimulus features and predicts how a person's brain would respond. We train the encoding model by presenting the person with over 10 hours of stories. And this shows us how their brain responds to thousands of concepts. We record these brain responses using fMRI. So semantic representations are widely distributed across the brain, and so the spatial coverage of fMRI allows us to capture these representations. And that gives us our brain responses. Next, if we want to model these responses, we need a numerical representation of the stimulus. And natural language is very rich, so we can extract different types of features in order to answer different types of questions. But in this work, we want to study semantic processing, and right now the best way to extract semantic features is using neural network language models. So a language model is a neural network. It's trained to take in a sequence of words and predict the probability distribution over the next word in the sequence. So this is a pretty simple, straightforward task, but it forces the model to learn about the meaning of the input. So during training, the model learns to extract this meaning and represent it in its internal states. So for us, we can take the words that the person heard, we pass them through our language model, and then we use the internal states as our semantic features. And this approach has been used by many different groups, and it's proven to be very effective at modeling brain responses. So now that we have the stimulus features and the brain responses, we can fit our encoding model. And as Joe showed earlier, this is just a simple linear regression where we predict how each voxel responds to the stimulus features. And we can evaluate the encoding model by using it to predict brain responses to new stories. It's like before we extract semantic features, we pass them through the encoding model to predict how the person's brain would respond. And then we score each voxel by comparing the predicted and the actual brain responses. So here I'm showing a flattened surface of the brain, and I'm coloring each voxel based on its prediction performance. And it turns out that most of cortex is well predicted during language processing. So all of these bright regions here are doing something systematic during language. So then we can dive deeper and ask what each region is actually doing. So we can use the encoding model to simulate how each voxel responds to a large set of new phrases. So if we look at this voxel near PPA, these are the top phrases based on the simulated responses. And just looking at these phrases, we can infer that this voxel cares about place names, like Central Park or Imperial College. If we look at this voxel near EBA, these are the top phrases. And that suggests that this voxel cares about actions, like tape down and open it up. So these are just two examples, but we can use this same kind of approach to map what every brain region cares about. And there's a lot of exciting work in our lab that's trying to do this. And if we can map these different regions of the brain, it opens up a lot of interesting new applications. So now we've seen what encoding models can do. So we can return to our original goal of decoding brain responses. Encoding and decoding are like two sides of the same coin, and we can use a framework called Bayesian decoding to turn our encoding model into a decoder. At a very high level, we can think of Bayesian decoding as a kind of guess and check. So let's say that we have these brain responses that we want to decode. First, we just start by guessing what the stimulus could be. So in our work, we want to decode language, so we can use our language model to generate possible word sequences. Then we can use the person's encoding model to predict how their brain would respond to each of these guesses. And as we saw earlier, this is something that the encoding model is quite good at. And finally, we can rank the guesses based on how well the predicted brain responses match the actual brain responses. So here, the sequence "I have a dog" is most consistent with the actual brain responses. So that's our prediction of what the person is thinking about. Okay, so that's a quick overview of how our decoder works. Well, let's see how well it does. So we can use our approach to decode brain responses while the person listens to new stories. So here, the person heard the words, "I didn't know whether to scream, cry, or run away. Instead, I said, leave me alone." And the decoder predicts, started to scream and cry, and then she just said, "I told you to leave me alone." So here, it exactly recovers these phrases in blue. At other times, the decoder paraphrases the stimulus. So here, the person heard, "I don't have my driver's license yet," and the decoder predicts, "She has not even started to learn to drive yet." So here, it's using different words, but it's capturing the same general idea. We can also decode brain responses during imagined speech. So here, the person imagined telling the story, "Look for a message from my wife saying that she had changed her mind and that she was coming." And the decoder predicts, "I thought maybe she would come to me and say she misses me." And in this last example, the person imagined going over a stream and seeing some log buildings. And the decoder infers that the person walked across a bridge and gets that they see a building. So those are just a couple of examples of what the decoder can do. The decoder is far from perfect, but it's clearly picking up on something. And we think that it'll improve as we get better models and collect larger data sets. But a more fundamental limitation right now is that the decoder relies on this large and expensive MRI scanner. And that makes it unsuitable for a lot of practical applications. So we want to adapt our approach for more portable devices. And we're really excited about DOT since it's a very close surrogate to fMRI. Obviously, we lose some amounts of spatial coverage and resolution, but we can ask, like, how good is good enough for what we want to do? And this will show us how far we are from portable decoding, and also how we might optimize our DOT systems in order to get us there. So first, we looked at how much our decoder relies on spatial resolution. So here we simulated the spatial resolution of DOT by smoothing our fMRI data. And then we trained and tested our decoders on the smooth data. And here I'm showing decoding performance for different levels of smoothing. So we found that smoothing the data lowers decoding performance. This is obviously unsurprising. But what was surprising is that decoding performance was still much better than expected by chance. And this suggests that the spatial resolution of DOT could be good enough for us to decode meaningful information. If we can actually get this level of decoding performance on real DOT systems, that would be a very promising starting point. Then we also looked at how much the decoder relies on spatial coverage. So like I said earlier, semantic representations are widely distributed across the brain. And so we want to make sure that DOT is able to access these representations. So on the left here, I trained an encoding model on our fMRI data, and I used it to map the broad semantic categories that are encoded in each brain region. So for instance, social concepts are represented in these red regions, visual concepts are represented in the green regions, and so on. On the right here, I'm applying the field of view mask from one of the Culver Lab systems. And so this removes the regions that we can't access using DOT. And we found that the DOT field of view still covers most of the broad semantic categories. So most of the colors up here are still represented somewhere in the field of view. So even though the field of view is limited compared to fMRI, we think that the semantic representations might be sufficiently redundant for us to capture them using DOT and decode some kind of meaningful information. So based on these results, we are really excited to start testing our approach in actual DOT systems. And as part of these efforts, we're also really interested in aligning our DOT data with our fMRI data. So as Alex mentioned earlier, DOT and fMRI each have their own strengths. And so we think that learning and alignments between these modalities can help give us the best of both worlds. So with that, I'd like to thank my co-authors and collaborators at UT Austin, and we've been really fortunate to work with Joe's group at Washington University. Thank you.